We have seen a number of examples for ordinary differential equations. In some cases, those differential equations had explicit solutions that we could write down. And in other cases, we had no explicit solution, but we could conclude from the background in physics that the differential equation has a solution. After all, if we've got an ordinary differential equation that models a process in physics or biology, if the model is any good, then certainly the differential equation is going to have a solution, which is not a rigorous argument, but sometimes might be helpful. However, from a mathematical perspective, we would like to have a rigorous understanding of whether a differential equation has a solution or not. It would be great if we just could look at the formula for a differential equation and could immediately tell that it has a solution. And then again, even if a differential equation has a solution, it is not even clear whether the solution is unique. In this video, we will address these questions, whether an ordinary differential equation has a solution, and if yes, whether the solution is actually unique. And specifically, I'm going to talk about two major results in the theory of ordinary differential equations, namely the Peano existence theorem and the Picarlinolef Theorem. The Peano existence theorem establishes that initial value problem has a solution under very mild requirements. And the Picolindev Theorem has a bit stronger requirements on the ordinary differential equation, but if those requirements are met, then we can actually establish the existence of a unique solution. So the results that we're going to talk about apply to the Cauchy problem or the initial value problem. Let us bring this problem back to our awareness. So the Cauchy problem asks for the solution of an ordinary differential equation of first order, where we've got y prime of t equal f of t and y of t. And we have got initial conditions y at t naught is equal y naught. We would like to know whether that initial value problem has a solution only by looking at t naught and y naught, the initial condition, and of course on the right hand side of the differential equation. And it turns out that we can learn a lot about the existence of a solution if we know a bit more about this function f. So only by studying this function f, you can establish the existence of a solution and even the uniqueness of the solution, provided that certain requirements are satisfied by this function f. Let us begin with the Peano existence theorem. The theorem states the following: let f be a function from the real numbers and r to the n into r to the n, and suppose that function f is continuous. Furthermore, let t naught be a real number and let y naught be a vector on r to the n. Then there exists a number t1 that is greater than t naught, and also a differentiable function y defined on the interval from t naught to t1 and mapping into r to the n, such that this function satisfies y at t naught is equal y naught, and y prime of t is equal f of t and y of t for all numbers t between t naught and t1. So here in this context, the function f takes two arguments. The first argument is a real number and corresponds to time. And the second argument is a vector in R to the n, which corresponds to our variable y. The output of that function f is again a vector in R to the n. This function f corresponds to the right-hand side of the initial value problem. And then we've got t0, which is our time where we set up the initial condition. And we've got y0, which is the value at the initial condition. What this theorem says is, if I've got this initial value problem, y to t0 is equal y0, and I've got the differential equation with that function f, y prime of t is equal f of t and y of t, then as long as this function f is continuous, then the initial value problem has a solution at least for some time after t0. So there exists some time t1, and the function y is defined for any time between t0 and t1. And to put it more loosely, if f is continuous, then the initial value problem has a solution for some time, at least for some time. Let me also remark the number n here, which is the number of components of y, is precisely the number of variables that we have in our system of differential equations. So for example, if you've got a first order ordinary differential equation in a scalar-weighted function, then of course n is equal to 1. But more generally, we're interested in systems of ordinary differential equations. The Peano existence theorem is useful because it has very mild requirements on the function f. So in many cases, you might say, okay, if the function f has a formula, then it is continuous. As usual, let us discuss a few examples. So in our first example, we have got the differential equation y prime of t is equal y of t times the sine of y of t times exponential of y of t. And we've got the initial condition y of 1 equal 2. Now, okay, the right-hand side here can be conceived as a function in t and in y, and the function f of t and y has the formula y times sine of y times exponential of y. And certainly that function here is continuous in both in t and in y. In fact, it doesn't even depend on t. And what we conclude is that this differential equation with those initial values here has indeed a solution. So t0 is equal to 1 and y0 is equal to 2. And the solution certainly exists for some time. So it might happen that the differential equation blows up, but at least for some time after 1, the solution exists. Example number 2. Let's take a look at the differential equation y prime of t equal t squared times cosine of y of t, with initial condition y at 0 is equal to 1. The right-hand side here can be conceived as a function in t and y, and that function is f of t and y equal t squared times cosine of y. Again, we can easily see that this function here is continuous in t and in y. And the Peano existence theorem now tells us that this differential equation with those initial values here, y at t0 equal y0, has a solution for some time after 0. So the function y is defined at 0 and for some time after 0. In those examples, number 1 and 2, we know that the solution exists for some time after the initial condition, but we cannot tell from the Peano existence theorem how long the solution will actually exist. It might be that the solution actually exists forever, but it might also be that like we see the solution blow up after some time. Now, in fact, in example number 3, we have got an explicit solution, and we can verify that that solution certainly blows up. Let's take a look at the differential equation y of t equal y of t square with initial condition y naught equal 1. Okay, we can easily check that the right-hand side is a function in t and y, namely f of ty equal y square. Certainly that function is continuous in t and in y. And we have actually already seen a solution for that differential equation with that initial condition, namely y of t equal 1 over 1 minus x. And as you remember, the function y of t at t equals 0 assumes the value 1, and then it grows very fast. In fact, it grows so fast that at t equal 1, we already have a singularity. It goes up to infinity. So what the theorem tells us is that for some time after 0, the solution exists. So y of t is defined at 0 up to some time t1. In that case, t1 must be smaller than the number 1. In this case, we explicitly know that t1 must be smaller than 1. Example number 4 is a standard example in the literature and displays some interesting features. So let's take a look at the differential equation y prime of t equal 2 times the square root of the absolute value of y of t with initial condition y at 0 is equal to 0. And let's take a look at the right-hand side of this initial value problem. Then we see that the right-hand side can be conceived as a function in t and y. In fact, the formula for f of t and y is equal 2 times the square root of the absolute value of y. That function is continuous. As an exercise, I suggest you stop the video at this point and take a look at the right-hand side here, 2 times the square root of y of t. And I suggest that you sketch this. I suggest that you plot this function as a function of y, just to get an idea what this function actually looks like. When you've plotted this function, then you see that actually for this function is 0 at y equals 0. For positive y, it is 2 times the square root of y, but it is also defined for negative y. So if you plot the graph of the function, then on the right of the y-axis, you've got the graph of this 2 times the square root, and to the left of it, you've got the mirror image of that graph mirrored along the y-axis. Anyways, we can tell that this function f of t and y is continuous, and so the Peano existence theorem tells us that there exists a solution to this initial value problem, at least for some time. Now, this initial value problem has a very interesting feature, namely, it has an infinite number of solutions. I've written down a few solutions here. So, on the one hand, if we pick y equals 0, so y is just a constant function that is everywhere 0, that's certainly a solution to this initial value problem. Another possibility is a function that is first everywhere 0, but at t equals 0, it changes to t squared. That's example number B. Y of t is equal 0 for negative t, and for non-negative t, it is equal t squared. I suggest that you check by yourself that this function, the possible solution number B, that this function is actually differentiable and solves the initial value problem. Another possibility is number C here. Y of t equal minus t squared for negative t and 0 for non-negative t. Again, I'll leave it as an exercise to check that y of t actually is differentiable and satisfies that initial value problem. Now, these are not the only solutions. There are a number of others. In fact, our solutions have a structure that is outlined here in the graph here in the right bottom corner of the screen. At the beginning, the function looks like minus t squared and grows until it reaches, it looks like a negative quadratic function, like minus t squared or a shifted version of minus t squared, until it reaches 0 at some point, at some time t minus. Then it stays 0, and at some point t plus after 0, which is completely arbitrary, it decides to grow like a quadratic function again. T minus is some negative number or 0, and t plus is some positive number or 0. So as you shift t plus along the positive part of the x-axis, and as you shift t minus along the negative part of the x-axis, you discover an infinite number of possible solutions to this initial value problem. This phenomenon demonstrates that the Peano existence theorem, if it applies, then it guarantees the existence of the solution for some time at least, but it does not guarantee the uniqueness of that solution. The version of the Peano existence theorem that we have discussed so far is in some sense not the real deal, because there exists a slightly more general version which, however, covers some important cases of ordinary differential equations. Namely, as we might remember, if I write down the formula for the right-hand side of the initial value problem, it might happen that this right-hand side is not defined for all times t or all possible values of y. And this version here of the Peano existence theorem addresses this and generalizes our first version. So let A be a set. Let A be a subset of the real numbers times r to the n. So A consists of a collection of pairs of t and y. And furthermore, let t0 and t1 be two real numbers, such that t0 is smaller than t1. And furthermore, let rho be a positive number and y0 be some vector on r to the n, such that the following property is satisfied, namely the interval from t0 to t1 times the ball around y0 of radius rho is contained in the set A. Now let's suppose we've got a function f that is defined on the set A and takes values in R to the n. Let us suppose furthermore that this function f is continuous. Under those assumptions, there exists a number tau that is greater than t naught, and a differentiable function y defined on the interval from t naught to tau, mapping into R to the n, such that, on the one hand, for all times t between t naught and t1, the tuple t yt is contained in the set A, and such that also y at t naught is equal y naught, and y prime of t is equal f of t and y of t for all times t between t naught and tau. Well, this is similar to the previous version of the piano existence theorem, and the major difference is that the function f is not necessarily defined on all of the real numbers times R to the n, but only on some subset. What this version of the piano existence theorem tells us is that there exists a function y that is defined at t naught and then for some additional time up to time tau, which solves this initial value problem. Y of t naught is equal y naught and y prime of t is equal f of t and y of t for all times between t naught and tau. And it guarantees that for all times t, the tuple t and y of t is in the set A, which is the set where the function f is defined. What the first two lines here of the theorem tell us is that the initial conditions t naught and y naught are contained within the set A. They are contained within the set of admissible inputs for f. In fact, also the surroundings in some sense of t naught and y naught are contained in the set A. So if I move from t naught up to some time t1, which might be small, but still larger than t naught, and if I move from y naught at some distance, which is at most rho, and rho might be small, but it's still positive, then all the values I can get are still contained in the set A. The set A, in some sense, is the set of all admissible inputs for the function f. So the whole point of this generalized version of the piano existence theorem is to show the existence of a solution for an initial value problem for some time, even if the right-hand side is not defined for all possible values of t and y. We have seen such an example already. Namely, we had the differential equation y prime of t equal 1 over 1 minus t times 1 over y of t, with initial condition y naught equal 1. Now, in this case, the right-hand side is a function in t and y, namely f of ty is equal 1 over 1 minus t times 1 over y. And the initial condition is t naught and y naught equal 0 and 1, respectively. Now, this function f is not defined for all possible values of t and y. So we would like to have the set A of admissible inputs for this function f. And we can choose a set A as follows. Namely, it's all t and y for which t is not 1 and y is not 0. We only need to exclude the cases that t is equal 1 or that y is equal 0. And if we have excluded these two cases, then the function f is defined. Now what we can tell is that t naught y naught is indeed contained in the set A. And what's more, I can go from t0 up to some time t1, for example, 1/2. And I can go from y0, some distance rho equal 1/2. And still stay within the set A. For example, I could say, okay, take the interval from t0 equals 0 up to t1, which is 1/2. And I move the number y between 1/2 and 3/2. And for this set of parameters, I will still stay in the set A. Now, for this initial value problem, the Peano existence theorem now specifically states the following. Namely, there exists a function y starting at t0 up to some value tau, where tau is a bit larger than t0, mapping into the real numbers, and that function y is differentiable, such that on the one hand, for all times t from t0 up to tau, the pair t and y of t is still in the set A. So if I take t and y of t, I'm never gonna hit the case that t equal 1 or y is equal 0. That's not gonna happen, and I can take t and y of t and put it into the function f. And in fact, when I do that, for all t between t0 and tau, I get the solution for the initial value problem. Namely, that function y satisfies that y of 0 is equal 1, and y prime of t is equal f of t and y of t for all t between t0 and tau. We have seen that the Peano existence theorem can establish the existence of a solution for the Cauchy initial value problem under very mild conditions on the function f. We only need continuity of the function f. But we've also seen that there are initial value problems which satisfy the conditions of the Peano existence theorem, which have solutions, but in particular, they have infinitely many solutions. So for many applications, the Peano existence theorem is somewhat unsatisfying, because in many cases, we do have unique solutions to ordinary differential equations. It turns out if the function f in the Cauchy initial value problem satisfies somewhat stronger conditions, then the uniqueness of a solution can actually also be established. And that result is known as Picar-Lindelof theorem. What you see on the screen is the Picar-Lindelof theorem, and I've highlighted the differences to the Peano existence theorem that you've seen a few moments ago. The theorems are somewhat similar, but in the Picar-Lindelof theorem, we have got additional conditions on f. So again, the theorem reads as follows. We've got a set A contained in the real numbers times r to the n, and got variables t0 and t1, where t1 is larger than t0. And we've got times t0 and t1, where t0 is smaller than t1. And we've got a positive real number rho. And we've got a vector y0 in R to the n, with the condition that the interval from t0 to t1 times the ball around y0 with radius rho is contained in the set A. And again, we also have a function f, which is defined on the set A and maps into R to the n, which we assume to be continuous. In addition to the piano existence theorem, we also assume the following. Namely, we assume that there exists a constant L larger than 0, such that for all times from the interval t0 up to t1, and for all y1, y2 contained in this ball of radius rho around y0, we have the following inequality. Namely, the distance of ft_y1 and ft_y2 is at most L times the distance of y1 and y2. Formally, the Euclidean norm of ft_y1 minus ft_y2 is bounded by L times the Euclidean norm of y1 minus y2. With that additional condition, there exists a number tau larger than t0, and a differentiable function y over the interval from t0 to tau, mapping into R to the n, such that on the one hand, for all t between t0 and tau, we have that the tuple t and y of t is contained in the set A, and such that y of t0 is equal y0, and y prime of t is equal f of t and y of t, where t ranges between t0 and tau. And we also have that the function y is unique. So uniqueness means that when I know t0 and y0, the initial condition, then there exists one and only one solution to that initial value problem for some additional time after t0. This new condition here, which I've highlighted, can be interpreted as follows. If I fix the time t, and then I take f of t, y, and I shake the variable y a bit, then the change in f of t, y is bounded by L times the change in y. This is a somewhat stronger version of continuity. Now, for the sake of illustration, I'm also writing down here a scalar version of the Picarlinolef Theorem, where the function y takes values in the real numbers. The scalar-valued version of the Picarlinolef Theorem might help you to understand this continuity condition. The theorem reads now as follows. Let A be a set of pairs of real numbers. The first entry in each pair is time. The second entry is the value of y. And again, we let t0 and t1 be real numbers, where t0 is smaller than t1. And we let rho be a positive number, and we let y0 be a real number, with the following conditions, namely the interval t0 to t1 times the interval y0 minus rho till y0 plus rho is contained in the set A. You may think of it like I have got a time interval from t0 to t1, and I've got the interval around y0, and if I put these into a rectangle, one side is the time direction and the other side is the y direction, then that rectangle is contained in the set A. Now again, we let f be a continuous function which is defined on the set A. And the continuity condition is now the following. We suppose that there exists a positive number L such that for all times t in the interval from t0 to t1, and for all y1, y2 in this interval, the interval from y0 minus rho to y0 plus rho, we have the following inequality, namely the absolute value of f of t y1 minus f of t y2 is bounded by L times the absolute value of y1 minus y2. With that condition, we can conclude the following, namely there exists a positive number tau larger than t0, and a differentiable function y, which is defined on this interval from t0 to tau, mapping into the real numbers, such that on the one hand, for all t from t0 to tau, we have that t, yt, this pair is contained in the set A. So in particular, t and yt can be used as input for the function f. And furthermore, the function y satisfies the initial condition, y of t0 is equal y0, and it satisfies the differential equation. For all t between t0 and tau, you've got that y prime of t is equal f of t and y of t. And again, the function y is unique. So if I know this differential equation and I know that f satisfies the continuity condition, then for any choice of t, naught, and y naught, I have a unique solution for this initial value problem. I believe it will be helpful to illustrate this continuity condition. In fact, this continuity condition is stronger than the usual continuity. Typically, a function that is continuous will not satisfy such an inequality. But there's a large class of functions for which this inequality is actually satisfied. For example, we can apply the Picarlinolef Theorem, the scalar version, if the function f is differentiable in y, and the derivative is uniformly bounded for all ty from this rectangle t0 till t1 times y0 minus rho till y0 plus rho. So to check that the Picolindev Theorem can be applied, we can take the derivative of f in y. We check that the derivative actually exists for all t and y. And then we check that for all ty from this rectangle, this derivative of f in y is uniformly bounded. Now to see that, we just recall the fundamental theorem of calculus. So let us take f and fix some time value t. F, when the time t is fixed, is only a function in the second variable y. And then the fundamental theorem of calculus tells us that f of t y1 minus f of t y2 is the same as the integral from y1 to y2 of the derivative of f in the second variable. Now, if I take the absolute value on the left-hand side and the right-hand side of this fundamental theorem of calculus, okay, on the left-hand side, I got the absolute value of f of ty1 minus f of ty2, which is the left-hand side of this continuity condition in the Picarlinolef Theorem. And on the right-hand side, I can bound this integral above by the maximum of the derivative of f in the second variable taken over all times t from t1 to all times t from t0 to t1 and all s from y1 to y2. And all that, this maximum value of the second derivative is then multiplied by the length of this interval, which is y2 minus y1. So in this context here, this maximum of the second derivative is my quantity L. So that sounds pretty good. We've got a large class of differential equations for which the Picolindev Theorem establishes the existence of a unique solution for some time. For the sake of illustration, let's apply the Picolindev Theorem to the following initial value problem. We have y prime of t equal t squared times the cosine of y of t, and the initial condition y of 0 equal 1. So in this formalism we have t naught equal 0 and y naught equal 1. Okay, to apply the Picarlinolef theorem, we need to pick some time t1, which is larger than t naught, and we try the following. Let's say t1 is equal, well, just 1. And we also need to pick some positive number rho. In fact, the choice of rho doesn't matter here. Let's just pick rho equal 1. And let's see whether we can apply the Picolindev. So first we check that y of that. So first, what is the function f here? F is t of y equal t squared times cosine of y. And we check, okay, also this function f is defined for, well, all times t between 0 and 1. And for all y from this interval of radius 1 around y naught. So actually, y in this case is taken from 0 and 2. Okay, it's defined for all the values for t and y taken from this interval. As a reminder, this interval here from which you take t, which is just t naught, t1, and the interval from which we pick y is just y naught minus rho to y naught plus rho. Okay, one condition is that f is actually continuous, and that is indeed the case. It's very simple to see here. And the other condition is there exists L greater than 0, such that for all t taken from this interval from 0 to 1, and all y1, y2 taken from this interval from 0 to 2, we have that t square times the cosine of y1 minus t square the cosine of y2. If I take the absolute value of the difference, it's bounded from above by this constant L, which we try to find, and the difference of y1 minus y2, absolute value. So how can I establish such a constant? Well, one possibility, just taken from the previous remark, is that the left-hand side here, t squared times cosine of y1 minus t squared cosine of y2, absolute value, is bounded from above by the maximum where t is taken from t0 to t1 and y is taken from y0 minus rho up to y0 plus rho. And we take the maximum of the derivative of f and y, which happens to be t squared times sine of y. Actually, there's a minus, but since we take absolute value, it doesn't matter here. That is multiplied by y1 minus y2. So is this expression here actually bounded? Well, it is, because if I take t squared with t taken from 0 to 1, okay, this t squared is certainly bounded from above by 1. And the sine of y is certainly bounded from above by 1 again. So what that establishes is the following. We get that f of t y1 minus f of t y2 is bounded from above by y1 minus y2. So that satisfies, that provides all the conditions we need for the Picarlinolef theorem. Before we proceed, just for practice with inequalities, let's also do a different variant of finding this constant L. I take this difference t squared minus cosine of y1 minus t squared cosine of y2 okay, I can factor out the absolute value of t squared times absolute value of cosine y1 minus cosine y2. Okay, I find this guy here is bounded from above by 1 because t is taken from the interval from 0 to 1. So this is bounded from above only by the absolute value of the difference of cosine y1 and cosine y2. And again, using the fundamental theorem of calculus, I can find that this is equal, this is bounded from above by the integral from y1 to y2 of minus sine of s ds. Takes the integral and takes the absolute value of that, which certainly is bounded from above by the integral from y1 to y2 of the absolute value of sine of s ds. And okay, so sine of s is certainly bounded by 1. So the absolute value is certainly bounded by 1. I find that this is bounded from above by y1 minus y2, which again leads me to the constant L equal 1. Now, anyways, no matter how we establish this inequality, the Picarlinolef Theorem applies. So the differential equation y prime of t equal t square cosine of y of t with y naught equal 1 as initial condition has a unique solution. Y of from 0 to some number tau, where tau is some positive number. Let me emphasize that the choice of T1 and the choice of rho here is a bit arbitrary. There's no particular way to finding them. You just need to make a good guess. Generally, we can pick T1 as small, as close to T0 as we want, and we can also pick rho as small as we want, as long as this helps us to establish the relevant conditions here. The Picolindev Theorem tells us that the solution exists for some time starting at T0, which is 0 here, up to some positive time tau. We have not yet established how large this tau can actually be. So this does not tell us yet whether the solution exists for all times. Maybe I've got a solution that can be extended to infinity. Or maybe there's a finite time where the function blows up. So maybe tau can be chosen arbitrarily large actually, or maybe there's a maximum value of tau that is possible, and as we get closer and closer to that point in time, the solution blows up. The Picarlinolef Theorem does not tell us yet which of these two possibilities applies. Let us revisit that example where we had an ordinary differential equation and initial conditions such that we have an infinite number of solutions. since we've got an infinite number of solutions here, there must be something that prevents us from applying the Picarlinolef theorem. If the Picarlinolef theorem would apply here, we would get a unique solution. So something must prevent us from applying the Picarlinolef theorem. So we have seen that the Peano existence theorem can be applied. So probably we can, so probably what prevents us from getting a unique solution is that the right-hand side of the differential equation does not satisfy the continuity condition of the Picarlinolef theorem. So indeed, if you take a look here at the right-hand side, which can be written as a function f of 2y equal 2 times square root the absolute value of y, one can show that this does not satisfy the continuity condition. Let us take a look at the sketch of this function y mapping to square root of absolute value of y. I've sketched the function graph here both for negative and positive values of y, but actually it's sufficient to only take a look at the positive values of y. So as you can tell here, this function is not differentiable at 0. And okay, it is still differentiable away from 0, but as we get closer and closer to 0, the slope of the graph becomes infinity. So in our example, we have that y0 is equal to 0. And okay, let's just pick any row greater than 0, some positive row, and let's take a look at this interval from from y0 minus rho up to y0 plus rho. Let's say I pick y1 is just my y0, and I say I pick y2, some real number from this interval close to 0. Okay, remember y0 is 0 here. So in that case, the difference of square root y2, absolute value square root y2, minus square root absolute value of y1 divided by y2 minus y1 absolute value. Okay, is that bounded from above by some constant L? Well, it's not. Because, okay, y1 is actually 0 and y1, this absolute value and takes the square root is also 0. So what I get is basically square root of absolute value of y2 divided by the absolute value of y2. And as y2 gets closer and closer to 0, this quotient here actually explodes. And you can see that here in like, if y1 is equal to 0 and y2 it's closer and closer to 0, then this slope here gets closer and closer to infinity. Just imagine that this point moves on the graph. The slope is gonna go into infinity. That just reminds me of the fact that the limit as y gets to 0 of square root of absolute value of y divided by absolute value of y diverges to infinity. So the inequality that I require for the Picolindev theorem does not apply here in this example. So the Picolindev theorem cannot be used to establish the existence of a unique solution for that differential equation that we had. which is perfectly in line with our observation that this differential equation, that this initial value problem, does not have a unique solution.